I start recording. If you have an objection or any idea, this is the right time to say your opinion. You say in Korean. I think I must be getting old because I never made such a mistake. But so sorry about that. Otherwise, I think the quiz problems are expected, right? So I give a hint about 2, 3, 4, 4 by 4 matrices, right? And I hope it's not too difficult. And it would be a good practice. So let's a bit more about unit matrices. So say A for given matrix, omission matrix, we already know that we have two eigenvalues, plus and minus, right? Lambda 1 equal plus 1, minus 1, plus 1. Lambda 2 is minus 1. And eigenvectors, normalized eigenvectors are 1i, and we have the following properties: lambda 1 plus lambda 2 is identity, and lambda 1 minus lambda 2 is A, right? This is called the spectral theorem. We can define new matrix. We can new matrix U such that U is lambda 1, lambda 2. So this is a new matrix made over eigenvectors. That is so this is a matrix that composes pointer 없지. 잠깐만. So this is actually the matrix that is made over column vectors over eigenvector 1, just arranged this way. And let's just see what take a joint. A joint of U is a transpose and complex conjugate, right? You transpose first and complex conjugate. Then it becomes square root of 2. When you make a transpose, the column becomes row. So 1i becomes you still need to take a complex conjugate. Okay, so let's just repeat this. 1i, 1 minus I. And if you take a complex adjoint operation, 1 minus I, 1i. And let's see what happens if you just multiply u dagger u. So it becomes 1 over 2. If we multiply this way, what happens? 1 plus minus I times I is plus 1, right? So it becomes 2. And this becomes 1 plus minus I times minus I, 0. 1i, 1 plus I square, 0. Finally, this, 1 plus I times minus I, 2. Very good. It becomes 1, 0, 0, 1 identity, right? How about if you just change the order? U dagger. Very special case. Come on. Thank you. One I minus I square root of 2, 1 minus I, 1 I becomes this one. Simply 1, 1 plus 1, 1, 2, right? So this becomes 2. How about this? Minus I plus I, 0. This. I plus minus I is again 0. Finally, I times minus I plus minus I times I, 2. Identity, right? So we can find that U dagger is same as U inverse, right? And we call this kind of matrices unitary matrix. And we call this unitary matrix. Yeah? Oh, sorry. So this particular matrix, when you take adjoint, and if you take the become an inverse matrix. This matrix is called unitary matrix. Then what we can do is so U square root of 2, 1I, 1 minus I, U integral square root of 2, 1 minus I, 1I. Let's see what happens if U integral A U. So we multiply U integral to A and U. Square root of 2, 1 minus I, 1I, 0 minus I, 0, square root of 2, 1I, 1 minus I, let's try to multiply this first. So it become 1, right? This minus I, this minus 1, this, again minus I. Let me check. This become 1, right? Minus I times I is 1. And this become minus I, this times this, minus 1, this times this, minus I. And 1, 1, I minus I. It's an interesting result. It becomes 1 plus 1, 2, right? 2. this times this. I 1 minus 1, 0. Minus 1 plus 1, 0. Finally, minus 1, minus 1, minus 2, right? 1, 0, 0, minus 1. So this is basically lambda 1, 0, 0, lambda 2. And we call this matrix as D. It's diagonal matrix. Or A become U, T, U plus. So we call this principal axis theorem. Or quadratic form. Same meaning. So if A is a Hermitian matrix, this is a bit of a theoretical part, but very easy to understand for 2x2 system, right? So it's just A is Hermitian matrix. With lambda 1, lambda 2, lambda n as eigenvalues. Lambda 1, lambda 2, lambda n, normalized eigenvectors. Then we can define U as lambda 1, lambda 2, unitary matrix, and let's say T is a diagonal matrix. Then A can be written as U, T, U diagonal. And we call this principal axis theorem. So we have seen two theorems so far, spectral theorem and principal axis theorem from the Hermitian matrix. Then you can have interesting properties that a square. A square is u t u 제거 u t u 제거 What happens if multiply u 제거 with u? It's identity, right? It's because it is unitary matrix. Become identity. So it becomes u t I t u 제거 u t square u t. So we can do the same thing, etc., a to the n u t to the n u 제거. So this is another way of calculating higher order matrix product. So you can either use spectral theorem to calculate the u and a to the n, or another method is to use the principal axis theorem to find the unitary matrix out of the eigenvectors, and then you obtain the forms, which is so much similar. So depending on the occasion, you can use either way. And the question is, I only showed this relationship only for 2 by 2 so far, right? So let's try to see if it holds for the larger matrix. So let's see. Let's try to see 3 by 3 and see what happens. Bit of practice. So if we are ready, I can move to the next page. So say A 1 1 0 1 0 1 0 1 1. We have studied this matrix previously, right? And anybody remembers eigenvalues and eigenvectors? Probably not, right? But you can just refer to the previous lecture note. I do remember lambda 1 is minus 1, lambda 2 is plus 1, lambda 3 is plus 2, lambda 1 is, I think it's 1 over square root of 6, 1 minus 2, 1. Lambda 2 is square root of 2, 1, 0 minus 1. Lambda 3, square root of 3, 1, 1, 1. Let's check. Right. So U matrix is lambda 1, lambda 2, lambda 3 is 1 over square root of 6 minus 2 over square root of 6, 1 over square root of 6, 1 over square root of 2, 0, minus 1 over square root of 2, 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. If we take a joint, I think that the rest of the process, you just need the patience. So column becomes row. So square root 1 over square root of 6 minus 2 over square root of 6 and 1 over square root of 6 square root of 2, 0 minus square root of 2. copy. And paste. Let's move to the next page. Can I move on? Uh-oh. Oh, it didn't, somehow it didn't work. Okay, let's just start from the beginning. U 6 some strange. Sometimes it works, but sometimes it doesn't work. Cut and paste, I mean. Whiteboard. So, how about U, tag or U? It complicates the calculation, it looks like. So this. So let's try the first one. 1 over 6 plus 4 over 6 plus 1 over 6. So that is 6 over 6, right? So equal to 1. How about this? This is 1 over square root of 12 minus 1 over square root of 12. So if you add them together, what happens? 0, right? How about the other one? This is 1 over square root of 18 minus 2 over square root of 18 plus 1 over square root of 18. So if you sum all three terms together, what do you get? 0, right? Good. Good. How about this too? Okay. 1 over square root of 12. This is a 0. This is a minus square root of 12, right? So again 0. How about these two terms? This 1 over 2 plus 1 over 2. No. Right. 1 over 2 plus 1 over 2. 1. How about third term? 1 over square root of 6 minus 1 over square root of 6. Again, 0. This may be a bit complicated. The first term is 1 over square root of 18. Second term is minus 2 over square root of 18. Third term is 1 over square root of 18. So if you add them all together, we get 0. This and this, 1 over square root of 6, this is 0. This is minus 1 over square root of 6. Again, 0. Finally, 1 over 3 plus 1 over 3 plus 1 over 3. 1. Identity, right? Good. Perhaps u times u dagger, I can give you as a homework. You can do it at home. Probably identity, right? But just do it at home. So we just learned that you can make a unitary matrix out of the normalized eigenvectors. Just arrange it as a column. What happens? U dagger A U. A was 1 1 0 1 0 1 0 1 1. U was square root over 6 minus square root over 6 over 2. Square root over 6, 1 over square root of 2, 0, minus square root of 2, square root of 3, square root of 3, square root of 3. This is square root of 6, 6, 6, 2. This and this. This is minus 1 over square root of 6, right? Our second term, 2 over square root of 6. Third term, minus 1 over square root of 6. This and this, square root of 2. This and this, 0, right? This times this, 0, right? How about this times this, minus 1 over square root of 2. This and this, 2 over square root of 3. This and this, 2 over square root of 3. This and this, 2 over square root of 3 times square root of 6 2 0 You just need to be patient. This and this. So the first term, minus 1 over 6. Second term, minus 4 over 6. Third term, minus 1 over 6. So if you add them all together, what happens? Minus 1 over 6, minus 4 over 6, minus 1 over 6, minus 1. Right? Second term, I think it's obviously 0. Right? So we have this and this minus 1 over square root of 12, 0. This is plus 1 over square root of 12. So we have 0. Third term, let me see. Third term, this and this. Obviously, minus 1 over square root of 18. 2 over square root of 18 minus 1 over square root of 18. Again, we have 0. This and this. 1 over square root of 12, 0, minus 1 over square root of 12 is 0. Second, this is 1 over 2 plus 1 over 2. So 1, right? This times this is 1 over square root of 6, 0, minus 1 over square root of 6. So you get 0, okay? This and this. Two over square root of 18. It's 1, right? 2, 2, 2, 2, 2. So this is 2 over square root of 18 minus 4 over square root of 18 plus 2 over square root of 18. All, if you add them together, you get 0. Very good. Second, okay. 2 over square root of 6 minus 2 over square root of 6. Again, 0. Finally, this is 2 over 3 plus 2 over 3 plus 2 over 3. So if you add them together, it's 2 is 6, right? 6 divided by 3, 2. So the diagonal elements become just the eigenvalues, right? Minus 1, 1, 2. So this is a D matrix. So this principal X theorem works for 3 by 3 and supposed to work for n by 1, n, and etc. etc. So it's a very useful tool. So maybe you can have a chance to solve the problem with this principal X theorem maybe in the next quiz. Perhaps you can take a break for a few minutes and continue, okay? So let's continue, okay? So, So another example, we have new matrix X this is a new matrix. The sigma X is 0, 1, 1, 0. Sigma Y is 0 minus I 0. Sigma Z is 1, 0, 0 minus 1. And nx square plus ny square plus nz square is equal to 1. This is our constraint. Then this matrix is very interesting, right? So matrix N becomes NZ minus NZ, NX minus I NY, NX plus I NY. This is combination of Hermitian, the Pauli matrices. This matrix actually comes very often in quantum computing. So, may be useful. We need to check whether this matrix is Hermitian. Is NZ, NX minus NY, NX plus INY, right? Minus NZ is N. So we can see that Hermitian. A joint is transposed with a complex conjugate, right? The transpose is you just convert the column into row. This is Hermitian matrix. Eigenvalue. This is minus NZ minus lambda NZ plus minus NX square plus minus NY square, right? So this is basically lambda square minus NX square minus NY square minus NZ square. But I told you previously that we have this constraint, nx square plus ny square plus nz square is equal, we have set to 1. So this is lambda square minus 1 is equal to 0. So lambda is again plus 1 minus 1, right? So calculating the eigenvector is a bit complicated, but in some problems we don't actually calculate the eigenvectors. So let's say lambda 1 plus 1, and we don't know, but lambda 1 is some matrix. Lambda 2 is minus 1. Lambda 2 is some matrix. And for some applications, we are not going to explicitly determine this matrix forms. So let's try for some problems. we don't need know the explicit form of plus minus, because we know that plus plus minus minus is equal to identity, right? Is square mate n, spectral theorem, right? It's n matrix. So from this, plus plus, if we add them together, what happens? 2 times I plus n, right? And 2 times I minus n. So we know at least one thing. Plus plus is 1 plus I plus 1 over 2. Minus minus is 1 over 2 I minus n. If you want to calculate some function of n, say, let's say n to the n, simple case, n to the square. If you want to calculate n to the square, what happens? Simply plus 1 square minus minus, right? This again, identity, right? N to the cube plus 1 to the cube we already know the answer. What is that? Just n, right? When it's even order, you have identity. Using spectral theorem. Plus 1 to 3 is 1. Minus 1 to 3 is minus 1, right? So if you just use the spectral theorem, then it's n. So in some cases, actually you don't need to calculate all the explicit form of eigenvectors, but just use this completeness relationship and spectral theorem. You can do a lot of calculations to simplify the things. But something like if some parameters such as theta n to the square is a little bit different. That is theta square plus theta square, again theta square, right? theta n to the cube, what happens? Theta cube plus minus theta cube minus, right? So theta cube to the n, etc., etc. So this can be a very interesting thing. So maybe we can stop here and then. What if matrix A is not Hermitian? Can we use something similar to spectral theorem? Can we still have something similar to the spectral theorem? Answer, yes, if A is positive or positive matrix. So we are introducing a new concept called positive matrix. So any vector phi A is greater than 0 is called A is called positive. So under which condition A can be positive? So say psi A for any vector phi, then bra vector is phi times A table, right? It's transpose and complex conjugate. So psi times psi, which is always positive, right? If you make an inner product with itself, it is always positive, non-zero. But or that is phi A dagger is always positive. So this matrix is a positive matrix. Let's call this M. Adjoint of M is what? A dagger, A adjoint is A adjoint, A. Same as M, right? So M is a Hermitian matrix. then so this is a bit difficult subject. So I'll try to speak and go as slowly as possible. And if you have any trouble understanding, just let me know. So this is about time to slow down if you have difficulty following me. So everybody has seen that M is a Hermitian matrix, right? The positiveness is very important. So A is any matrix, not necessarily Hermitian. A, any matrix. M, A dagger A is Hermitian. So we can find eigenvalues, real, and normalized eigenvectors, vectors lambda 1. But there is one thing, M is positive matrix means all the eigenvalues are positive or 0. Right? Because it is positive matrix. So any eigenvalue has to be greater than or equal to 0. Because if we set any vector as some lambda I, then lambda I m lambda I is actually lambda I. It has to be 0, right? So this positive matrix, so all the eigenvalues are 0 or greater than 0. Then spectral theorem says M can be written as square root of I lambda I and have M this spectral theorem, right? And we have seen that M square lambda I square M to the n to the n, right? So you can continue this process and say some function of M, any function of M can be expressed as f lambda I, lambda I, lambda I. Can you accept this? Spectral theorem says M is lambda I times this. M square is lambda I square. We can continue lambda to the n is lambda to the n. If you continue this process, any function of fn can be written as multiplication of f of lambda I with this vector, right? This is if you extend the specular theorem using this way, I mean, you can actually accept this as if you can express function as a Taylor series, lambda square, then eventually we can represent f of n as eigenvalues, right? Then, if we accept this property, then we can even define square root of a matrix, square root of m. So simply square root of lambda I times lambda I. And here, the positiveness of a matrix plays a role because all the eigenvalues are supposed to be 0 or greater than 0. And you should have a positive function inside the square root. So, from specular theorem, you can see that all the power of n can be written actually as lambda I power of lambda I. And then you can just extend this concept into any function of a matrix, into function of eigenvalue with outer product. Then we can say square root of n can be defined as square root of lambda I times outer product. This is a bit difficult concept, but I think up to this point you probably need faith. You have to believe. This is an important step. Probably I can spend more time, like probably you have learned about Taylor series, right? In freshman mathematics. So this thing may be a little bit difficult, so maybe I'll just spend a little more time in the tour. Taylor series. Any function f can be written as fx0 plus x0 plus etc. Not familiar with this? You haven't seen this? Or sine x as x minus x to the cube over 3. You haven't seen this formula before? You have seen. Taylor series. Right. So, say f of x a0 plus a1x plus a2x squared plus, say, a3x4. 3. Say, if you can expand the polynomial expansion for any function, then the function of matrix also can be, say, a0i plus a1m plus a2m squared, a3m cubed blah, blah, blah. Then A0, this is identity matrix. So this is lambda I plus A1 to the lambda I plus A2 lambda I square lambda I. So we can just combine them together into this A0 plus A1 lambda I plus A2 lambda I square, etc., lambda I. And this is actually what? F of lambda I, right? So if you define some function as some constant A0 plus A1x plus A2x squared plus A3x cubed, etc., we just define the function this way. Then the functional matrix, we just replace 1 by I, x by m, right? Then each term can be represented by this. This is identity, so this is just put this way. M is a spectral theorem, and next term is lambda I squared, etc., etc. So if we can sum factor this together, we have A0, A1 lambda I plus A2 lambda I squared, etc., etc. This is function of lambda I. So we can say that this is a bit complicated concept. So try to review it at your home. So from spectral theorem, you must be familiar with the spectral theorem by now. Then any function of m can be written as f lambda I. Then you can even define m as square root of lambda I, and lambda I is greater than 0, so we can define square root, and because m is positive. Then unitary matrix U such that A U times square root of m. So any matrix A can be represented as a product of unitary matrix times square root of a positive Hermitian matrix. This is called the polar decomposition. So today's class could be a bit theoretical, so I'll try to proceed as slowly as possible. So the first question is how to construct a unitary matrix. That is the first step. But I will let you copy the screen. The first step is step number 1. But before I proceed, maybe it's convenient for you to practice some numerical example before I proceed. So before I go to mathematical details, let's start with the matrix A. Which is 11 minus 5 minus 2, 10. So let's say this is summation or not. A dagger 11 minus 2 minus 5, 10. Definitely not summation, right? So how about M? A dagger A. 11 minus 2 minus 5, 10. 11 minus 5 minus 2, 10. Eleven times 11 times 11 is 121. Plus 2 by 2 is 4, 125. 125. Minus 55, minus 20, minus 75. How about this? Minus, again, minus 55, minus 20, minus 75 again. This times this 25 plus 100, 125. M adjoint 125 minus 75. Commission, right? Let's see if all the eigenvectors are real. So, eigenvectors M minus lambda I 125 minus lambda 125 minus lambda square minus 75 square. So 125 minus lambda plus 75 minus 75. 200 minus lambda, 50 minus lambda equal to 0. So lambda is 50, 200. They are positive, right? So lambda 1 is 50, lambda 2 is 200. Eigenvectors. So lambda 1 is 50. So M, let's say lambda 1 is AB. M lambda 1 is 125 minus 75, 75, 125. AB is 50 AB, right? So minus 75b is equal to 50a. Minus 75a plus 125b is 50b. Basically, a is equal to b, right? So if we subtract 50a from here, 75a is same as 75b. Same as a equal to b. So we can easily say lambda 1 is square root of 1, 1, right? How about lambda 2? Just give you some time to copy. So I can proceed. Lambda 2 is 200. So maybe CG 125 minus 75 minus 75, 125. CG is 200 CG. That means 125C minus 75C is 200C. Minus 75C plus 125C is 200C. Oh, so what do we get? C is equal to minus C, right? Here. Anyway, we have, if you subtract this, 200 minus 125 is 75. So minus 75D is same as 75C. For here, minus 75C is same as 75D. So anyway, D is equal to minus C. So normalize the eigenvectors. Lambda 2, okay. Square root of 2, 1, minus 1. So, in order to define new unitary vectors, so we have solved this case. I'll just outline the next step and probably stop. Probably it's better for you to have some time to digest the material what you have covered today. But I will give you some outline for what is going to do next time. So, we are going to define, in order to find the unitary matrix U, we define a new vector psi I such that psi I A times lambda I. Then define EI as a square root of lambda I psi I. And from them, U is defined as EI lambda I. Why we are doing this, probably we can see more clearly next time. So I'm going to stop here today. And if you have any questions or trouble to understanding, or any other things, you can ask me a question or you can send me an email to my university mail. Maybe